And the ways in which we use hydrogen will create substances and the ways in which we use them.
Welcome back to Hydrogen Energy News Biz Interview Series. My name is Aleksandar Žeradjanin, and my guest today is Aleksandar Žeradjanin. He's a prominent researcher at the Max Planck Institute for Chemical Energy Conversion, specializing in electrocatalysis and hydrogen production. Dr. Zeradjanin's work involves advanced characterization techniques and innovative approaches to improve the efficiency and performance of catalytic processes. His contributions are pivotal in understanding and applying clean energy technologies. Aleksandar, welcome.
Good morning, Ernest. Thank you for the invitation. Yeah, it's a pleasure to be with you this morning. Yeah.
Can you give us a short introduction on who is Aleksandar Žeradjanin and your research?
Yeah, sure. Thank you. I'm originating from Belgrade University. Yeah, I studied chemical engineering in Belgrade, and during the third year, I came in contact with electrochemistry. Yeah, and this was an immediate moment that I somehow developed interest. In the very first lecture, my professor said, I find it very, very intriguing area. Then after finishing master studies, I moved to Germany, to Ruhr University Bochum, and I finished PhD. And after that, I was in several institutions, in Max Planck Institute in Düsseldorf, in Forschungszentrum Jülich, University of Bremen, Fraunhofer, etc., etc. So there was, in principle, process where I was working in different groups with the different professors who had different approaches, analytical tools, and institutions that are different in a character. Some of them are fundamental research, applied research, etc. But luckily, in all these groups, all these professors were interested in electrocatalysis. That is essential area for the energy conversion and storage. And somehow this allowed me to develop my own research profile. Certainly, I absorbed something from each of them. Yeah. And important, I had continuity because all of these people were involved in electrocatalysis, so I could continue my work in this period of 15 years. From 2020, I have a permanent position as a staff scientist and a group co-leader in Max Planck Institute in Mulheim an der Ruhr. It's an institute formed maybe 13, 14 years ago on a foundation of Fritz Haber Institute in Berlin as a strong physical chemistry background. And Mulheim has previously institute so-called Kohlenforschung that had long-standing tradition in industrial chemistry. Yeah, this is the place where it was developed Fischer-Tropsch process, Ziegler-Natta catalyst, and the last big thing was 3 years ago. We had a Nobel Prize winner, Benjamin List, for asymmetric catalysis. So it's a long-standing tradition in catalysis. It's a premier institute for fundamental research, but with the links to industrial chemistry. And the last couple of years, of course, the focus is electrocatalysis and hydrogen energy. Yeah, there are some other institutes dealing with the batteries, of course, and other conversion technologies, but we are focused on hydrogen. And in this subsystem for the hydrogen storage and utilization, we set priority first on the water electrolysis. Yeah, of course, we have interest in hydrogen storage and in fuel cells, but we try to understand first the efficiency of hydrogen production. In that direction, we took more fundamental approach. Yeah, we will talk about this today, but with practical implications. Yeah, so this is what we try to understand, and the answers that we are trying to give should be directly linked to improvement of efficiency in the real world, on a real scale. This would be like.
Can you walk us through your recent research? And you mentioned tunneling and some other important discoveries. So can you walk us through this?
Yes. So to understand maybe the motivation, how things developed, I can tell you in these terms. So during my PhD, we were developing the anode for chloralkali technology, yeah, to reduce energy consumption for chlorine production. And we were successful. We developed anode that was better 67 millivolts than standard. And this is on an annual level, maybe if you consider industrial electricity in that moment, 17, 80 million euros annually savings, yeah? And anodes arrived at testing of 3 years, etc. So this was a success, and I was very encouraged. And somehow the natural evolution was to apply this knowledge on water electrolysis, because chlorine evolution and oxygen evolution exhibit the same trends, activity trends on various oxides, yeah. But then during this process, we realized actually that there's a major challenges with oxygen electrode in water splitting, and with activity, yeah, the over potential is very high, but also with stability of materials, yeah. And working in this field for approximately 5 years, I realized that complexity is too high, because oxygen is the 4-electron process, yeah. And then I decided to go back, say, okay, let's follow the science of simplicity. Let's go to more simple reactions, yeah. And then I returned back to hydrogen, maybe 2016. I wrote one critical review, yeah, where I was analyzing the field, and then I identify a lot of gaps, a lot of misconceptions, a lot of views that are not based on experimental data, etc., etc. And from that moment, I start generating experimental data that I consider to be important, yeah, to fill these gaps. And during this process, of course, the new questions were opening. One of the most important things that I saw through experimental data in the last couple of years was that the classical notion that exists in catalysis, that we will accelerate the reactions by reducing activation energy or activation barrier, is not necessarily true. Yeah, that there are materials that are highly active and who have very high activation barriers or high activation energies. And in their case, if you recall Arrhenius equation, yeah, that is more than 100 years old, we have that besides activation energy and the temperature, yeah, rate constant is impacted by pre-exponential frequency factor. And this is a parameter that describes the successful collisions between the reactant and catalyst surface, yeah. And one of the consequences of this is that of investigating this phenomenon of pre-exponential factor, we saw actually that it's possible to pass through the barrier, yeah. So this is a phenomenon of tunneling, and that maybe the key to come to something that will look like a breakthrough in oxygen electrocatalysis or oxygen electrochemistry, that is essential challenge for us, is maybe to find ways how to control the pre-exponential factor. And we are on that road now for several years. We have some interesting results that are published. We have some other that are under revision. It is not easy because it's a bit conservative community, yeah. There are things that were supported for 100 years, yeah. And it looks logical. I don't want to disprove the logic that, yeah, it was important to reduce activation barrier. In some cases, this works pretty solid. But in some cases, doesn't work at all. So you have very active materials with very high activation energies, and their activity comes from pre-exponential factors. So they have unusually high number of collisions between the reactant and a catalyst surface. And of course, this can come also from the tunneling. This is the quantum phenomena, that protons and electrons are passing through the barrier instead of overcoming the barrier. So this is somehow the fundamental thing that is of central importance for us. And we have some other things, of course, that we're dealing with. Yeah, we deal also with stability of materials. We try to understand absorption in materials related to storage, etc., etc. But considering for electrocatalytic activity, understanding of nature of electrocatalytic activity, our central problem or central challenge is actually to understand how can we tune the pre-exponential factor. This is the current fundamental challenge. And of course, this will have direct implication on material design. Yeah, if you figure out this, because in catalysis in general, and in electrocatalysis especially, essential task is to establish structure-activity relations. This means we try to understand if we have, let's say, material with very high reaction rate. We have to find what parameter in the rate law is responsible for this. Then we have to find what interfacial property is responsible for this. And this is property that is strictly a result of interaction of electrode material and electrolyte, and then to correlate this with some material property that we can tune. This will be the complete structure activity relations that we know. If we have enhancement, where is it coming from and how can we tune it? And this will take some time, but I think that we are in a good way. Yeah, approach that we took, there are already a substantial number of people who respect that papers are getting citations, but of course we have also the stream of people who don't want to go that way. They would like to keep things as they are, despite evidently approach that is currently the state of the art is not giving the solution.
How far are we from that breakthrough? Talking about years.
But if I would say for the hydrogen reaction, it will take 5, 6 years, 7 years, I would say. For the oxygen, it will take the double. So approximately 15. Now then you need to implement this. So I believe realistically hydrogen energy will work between 15 and 20 years from now, really. This is what I have as a projection. I can be wrong, of course, because you have people who rely in approach. I try to have strategic approach to the research. There are people who are doing, who have like simple credos. They use serendipity. Yeah, let's try and let's see what will happen. This is okay. This is completely okay. But I think that for the challenges like this, like oxygen electrode, is practically the central challenge we have. I would say it's pretty complicated. You need to be really lucky to coincidentally find material that will be very active and very stable for this.
And then we come to critical materials and their availability. But also what I'm interested at is the scalability of such solutions in future. How scalable is it when you bring it out of the laboratory into the real world?
You see, there are the two types of reactions of interest for us in a principle. One of them are, like in electrolysis, gas evolving. So we generate the gas, and we have a gas consuming in a fuel cells where we consume the gas. In a principle, if you talk about the gas consuming electrodes, like in the fuel cells, it's much more easy to transport the results from the lab to the real scale. For the gas evolution, it's not so easy. Why? Because one of the consequences, if you have really good catalyst and very active catalyst, that you generate a lot of product, yeah, it's so-called oversaturation, that at the end results in a gas formation at the interface. And the product itself, the gas, is blocking the active sites. So it has self-inhibiting effect. And it's linked with ohmic drops, but the biggest problem is that you block the active sites, and in real systems, we drive the process with the constant current or galvanostatically, yeah? So when you push 1 amp through, let's say, 1 centimeter square of geometric area, but 95% of your surface is blocked with the gas, then the current is passing through a really small fraction of the surface. And this is really damaging for the long-term performance of the catalyst, yeah? So what we investigate on the low current densities in a lab has to be always tested industrially very carefully, because it can happen that from the stability point of view, it will fail. Yeah, but it will never happen that we have, let's say, good catalyst in a lab, very active, and it will not be active in a real surroundings, industrial setup. Yeah, simply doesn't work like that. Or that something is a bad catalyst in a lab and good in industry, also doesn't work like that. So we can find very active materials, have certain projection of stability, but they need to do testing. This is what they need to do, because we cannot occupy instrument for 3 years. This is what they need to do. And of course, if we can predict, we build our credibility on that way and mutual trust. And it's a proof that we understand things. If not, showing we need to learn more. Yeah, we also have good intentions. We don't want to waste their time, but we can offer what we know. Yeah.
Can you explain the impact of, sort of say, hydrogen hype in the last few years, and what does it bring in terms of research and in general?
It's a positive thing generally. We need clean energy. Yeah, we live in a world where, just consider that global energy efficiency is around 5%. At least it was a couple of years ago. I did not check recent data. So if you consider just this aspect, you can imagine what amount of heat is created due to irreversible exchange heat with the environment because of low efficiency. Just take that aspect. Yeah, so it's very bad. Plus we release gases. There are a lot of negative consequences for the environment. Hydrogen energy looks like an elegant solution. Yeah, and also, besides being clean, it's related with many big industries, ammonia production, chloralkali. So you have good presumptions to build infrastructure that is linked to industry, petrochemistry industry, etc. Yeah. So it has a potential to be gigantic thing, and technology, we can observe it as technology. All this, yeah, and electrolyzers, storage, fuel cells, all this is hydrogen technology. That can have an impact on a world that is big. Yeah, I would not exaggerate now, but we can say transformational. Yeah, it will be something that we never saw before. Yeah, of course there will be some problems there also. Yeah, for example, with the fuel cells, if we release water vapor in the cities, we can expect also problems with humidity. Yeah, so we have to look at this holistically, yeah, from all points. But it's generally very positive. It's good that we recruited a lot of people in the field from different areas: analytical chemistry, physical chemistry, physics, material science. So there's a big concentration of highly educated people. At the same time, there are some negative tendencies. Last couple of years, you can see almost a decade, a lot of papers that are overselling materials that are clearly cannot be used. Yeah, for the let's say water electrolysis, for oxygen evolution. Yeah? But this is somehow normal, I would say. Yeah, it's you can expect this, but also where is now the trick? The trick is to identify the good literature in this sea of literature. Yeah, you have thousands of papers. How you know? You can sometimes follow the logic of the good group. You know, okay, this professor is competent and his people show to be in continuity really good. Otherwise, it's not so easy. When I arrived to Germany, I remember for my PhD, I read all 400 publications on dimensionally stable anodes for chlorine. There was around 400 and something. Today, if you would like to read papers on oxygen evolution only that are annually published, it will be, very, very difficult to, yeah. So this is the challenge: how to identify the good things. Yeah, but if the process started, no one can stop this. Yeah, no one can stop this. So hydrogen energy, slowly, it will take some time, but it will get its place in the world, I believe. Yeah.
So, how do you address the challenges associated with hydrogen storage in metal hydrides, specifically regarding weight and capacity?
Thank you. This is an important question because there's a lot of debate how really to store the hydrogen. Yeah, and metal hydrides have relatively good energy density. They're not comparable with the fossil fuels, but they're not bad. They are much better than batteries, for example. Yeah, and I think that last couple of years there was this fascinating material, lithium borohydride, something like this. Yeah, that actually beat this DOE, Department of Energy, targets for 2025. I don't know. So it's possible, yeah, to go further there. Yeah, but what you can see is that what is a lithium boron hydride? So it's very rare materials again. Yeah, lithium is. There is a paper from Vesburg where he classified all the elements in periodic system into 4 groups, where only first 2 groups can be used to upscale energy technologies globally, yeah, while the other 2 groups are rare elements. And lithium belongs to these pretty rare elements. Probably boron is also, yeah. This is one problem. The second problem with hydrogen storage and improving this further is following. In catalysis, we are trying to search for so-called catalytic descriptors. These are parameters, or sorry, the material properties, that we can tune that will have impact, as I said previously, on some interfacial property, and then finally on total reaction rate. And if you would like to make analogy with hydrogen storage, you need to identify what property of material is responsible for absorption of hydrogen. Or, in other words, the question for any chemist in the world: why palladium is so unique? Palladium absorbs hydrogen enormously, more than any other metal. What property is responsible for that? And if you observe the various properties of for the metals, the cohesion energy, sublimation energy, melting point, work function, you cannot find a single one where palladium is unique, or at least we don't know what property is that. But there is something, it has to be, because it's absorbing enormously. So what I'm trying to tell you, if we want to talk about rational design, and rational design in the case of hydrogen storage in hydrides, we need to answer the first question: what is the descriptor of absorption? Theoretical chemist will tell you computational, it's free energy of hydride formation. This is thermodynamic consequence. It's not material property. So what property of material is responsible? And then if we establish this, or we learn, we can talk about design. In the meantime, we walk in the dark. So I believe that there's potential to improve this, but how they're doing it, I don't know, because there is no answer on a basic question that we would need to answer.
What advancements have been made in developing liquid organic hydrogen carriers, and how do they impact the efficiency of hydrogen storage and release?
For liquid organic hydrogen, this is something that there is a report in the literature, I think, from Wasserscheid from Erlangen. This is Forschungszentrum Juli Helmholtz Institute in Erlangen. They did this a couple of years ago. There was a material, I can tell you approximately the name, I'm forgetting. It's perhydro dibenzyltoluene. This is the name. So they reported pretty high energy density and high conversion efficiency, etc. But what is the problem with this? As I see it, just you see the name. I read you the name of the compound. It's a complicated organic compound. And to claim in electrochemistry or electrocatalysis that we can control selectivity for these kind of reactions, it's still too early. We don't have this knowledge. So the problem for me as electrochemist with liquid organic hydrogen is to control selectivity of these reactions. These are complex molecules, and if you observe one, let's say, big molecule that's approaching to the catalyst surface, he would need exactly with specific functional group to come in proximity, absorb, or have proton transfer, etc. So probability for this is not high. And electrochemistry generally, the scope of it, because we have two-dimensional reaction zone, electrode is practically two-dimensional reaction zone, is to produce small molecules, not the big molecules. And they used molecules that are, for me, a bit too complex. I'm not saying that this cannot work in some point. Maybe this is the solution on a long term, because you can store these liquids in the pipelines for gas, I would say, without major problems. So they are pretty flexible in that sense. But still, it's a complex field to claim that you can control. These are reactions of hydrogenation and dehydrogenation. But the molecules are very complex in my perception.
What methods have you found most effective for transporting and distributing hydrogen in gaseous and liquid forms?
But this for liquid, now what we mentioned, this can be one of the ways, if it functions one day, this liquid organic hydrogen or ammonia. There's also attempts. This is old idea of John Bockris to produce hydrogen in regions where solar flux is high and then produce ammonia, transport to Europe or whatever. This can be, but for me, personally, I'm favored mostly of the gas transport in the pipelines. You have in Germany the network of the pipelines around 12,000 kilometers for the natural gas. And now I have some discussions with colleagues from Open Grid, is the company that's responsible for that in Germany. We are discussing, because there are some corrosion problems there with also natural gases inside. So we're trying to understand how to overcome this, and if we would put hydrogen, what will change. But this will be excellent if this could work. Yeah, because you have already the pipeline infrastructure is there. It's a massive, yeah. And it's also, again, interesting, it's electrochemistry again, yeah. Corrosion is the challenge, yeah. How to beat the corrosion in that case. So this will be, I would prefer if this could work, because this will save us a lot of effort, yeah, if the pipeline can work. And of course, for this pipeline, in the future, or part of it or whatever, can be used also for the liquid fuels, yeah. There's no issue, yeah.
It's very interesting to hear that you're cooperating with companies on this. And how far along is this cooperation in general? Are the companies interested in, and how much do they participate in the research?
I think Germany is probably ahead of others in Europe in that sense. Yeah, Germany was investing a lot in fundamental research, and before this crisis, yeah, now and we have this war and all this situation that is very turbulent, but Germany was investing a lot, and in different sectors, and fundamental research and applied and in between. And the companies were these big corporations like Bayer, BASF, ThyssenKrupp, Siemens. They are participating in the projects, and especially these projects related to the ministry, BMBF, Federal Ministry for Education and Research. Yeah. Usually they require industrial partner. So the nature of the project is like this, that you need to have industrial partner, otherwise it doesn't function. Yeah. So it's a stimulative way, yeah, to come in contact and see the way of thinking and exchange ideas and knowledge. Yeah. Of course, they also have their own IP they need to protect. I can understand it, but usually it's very beneficial. Yeah. So I had with several companies contacts, and we had some projects, and it's a good exchange. They are open. We learn from them, they learn from us, and I think they have pretty solid teams. Yeah. So I think the overall impact of the corporate sector here is pretty positive. Yeah. I would say that the issue that we have is maybe education. And why is like that? Because the area of electrocatalysis is very complex. In one of book chapter that I published in Encyclopedia of Solid Liquid Interfaces, I was just giving one small scheme, identify, let's say, 6 areas that are relevant for electrocatalysis, that you can be, let's say, called expert in electrocatalysis. And you cannot find person today who can cover all this. Maybe 1-2 areas. So I think essentially, if you have the exceptional challenge, you need exceptional people. Yeah. And to do that, what I was proposing last couple of years is a co-supervision. The 2 or 3 professors are surrounding one student who is motivated, driven, talented. Yeah. Not everybody can do that. But in that way, they can transfer human knowledge, they can build intuition with time, and then be capable to deal with this. Because we have, let's say, oxygen electrochemistry, we deal for decades, and everybody failed trying to improve it. Yeah. So probably we need better education in that sense. Of course, I'm supportive of artificial intelligence. All this is okay. You remember the case with Kasparov, yeah? In the first, when Deep Blue played against Kasparov, in the first match was 3 victories for Kasparov and 2 draws, and then modified version of Deep Blue beat Kasparov. I think it was 2-1, something like this. I forget exactly, but so artificial intelligence can help, no doubt about that. Yeah, but I think we need people who will be better than us. Yeah, new generations who will be better than us.
Probably paired with a proper AI, that might happen.
Yes.
How has your research contributed to improving the durability and performance of PEM fuel cells?
I was lucky when I arrived to Bochum and also in Düsseldorf in Max Planck. There was a project on fuel cells exactly in that direction. And first, what I did during the PhD as a parallel project, I developed methodologies based on microelectrodes, where you can monitor peroxide as an unwanted product of oxygen reduction that attacks the membrane and the carbon and whatever. So I noticed on these materials that are in hype, then metal nitrogen carbon composites for oxygen reduction in alkaline media or in acidic, also some people try to use. They actually, because of wrong way how people use rotating ring disk electrode, they were getting to misinformation about number of exchange electrons and peroxide produced. Yeah. So I developed methodology where I saw actually that peroxide is predominant product on these materials, and that you cannot protect it from the corrosion. Yeah. It will be very, very difficult. Yeah. That they can change selectivity on these materials. And I think they're also pretty abandoned today. This was the first part, like important insight. The second was when I moved to Düsseldorf, they had advanced analytics for corrosion studies, identical location, TEM. So you can observe exactly the same position before and after electrochemical treatment, and then you can separate the degradation mechanisms. There are 5 basic degradation mechanisms for the fuel cells. So you can exactly follow, did you have agglomeration? Did you have carbon corrosion? Did you have so-called Ostwald ripening or dissolution? So you can literally see like a movie. Yeah. And also then we dealt with in situ dissolution studies. Yeah. Where you can see how much material dissolves during oxygen evolution. And you can make the projection, yeah, on a time scale that is relevant. And we try to understand these degradation mechanisms with this tool. So it was, I was lucky to be, when I was in Düsseldorf, I think there's Karl Meyerhofer was then group leader there. I was a postdoc. He was the one who really pushed stability studies. Yeah. And this was important. That awareness of that was raising with time. He was then relatively young, but he had clear idea that this is important to be investigated. And so I was in a group that had excellent analytics, and so we gained a lot of insights in that field. Some of them created feedback how to improve the materials. For example, I was analyzing how with morphology design I can accelerate gas evolution. Yeah. And on that way to minimize dissolution of the catalyst. So this was, let's say, something that worked pretty well. And also we had the ways how to design morphology of the electrode to accelerate gas evolution. So yeah, it's important to have good analytics, definitely.
Talking about the catalysts, can you elaborate on the recent advancements in catalyst development for hydrogen production and their impact on efficiency?
But this is an important question. Yeah. If you observe, let's say, the tendencies, you have the review from Stolten, from Jülich and his group, maybe 10 years ago. Yeah. So you can see the developments from 70s till that point. Yeah. And you will see that it's more or less the same materials are used. Yeah. On anode and cathode, in acidic media, also in alkaline media on anode and cathode. In acidic media, because we use noble metals, it's important to reduce the loadings. And this is where the progress is made. Yeah. In electrolyzers, they reduce loading a lot on both sides. And in the case of fuel cells, just to mention, it's important, it's not hydrogen production, but it's somehow a linked system. They went on higher current densities. Yeah. So let's say voltage was around 0.7 volt on 1 amp per centimeter squared 20 years ago. Today, you can go on 3 amps on the same voltage. Yeah. So they increased the power output almost 3 times. Yeah. So there was mostly progress was coming from reducing of the loading of noble materials and improving the mass transport in the system. Intrinsic catalytic properties of materials, there was no really improvement. Some significant that we could say, okay, this is, yeah. So this was relatively modest, to be honest. And especially this tendency to use non-noble materials, try to design them in a way that they behave like noble, this ultimately failed. Yeah. So we still don't know how to produce noble material out of non-noble material. We don't have this knowledge, if it's possible at all. I believe it's possible, but yeah, let's see with time. But from that perspective, it's so if you observe, from these contributions to the energy consumption, you have intrinsic activity, mass transport limitations, atomic drops, etc. There was a lot of progress in, let's say, generally engineering area. Engineering area gave a lot of, while tuning of intrinsic activity of materials not so great. Yeah.
And what new materials or designs have significantly improved the efficiency of water electrolyzers?
But this is what I just said, so this is, there is no replacement from iridium oxide on anode, yeah? There is no material that really, ruthenium oxide is better, intrinsically more active, but is unstable. And on a cathode, there were some improvements. People propose materials like molybdenum sulfide, yeah, that to replace the platinum, although our potential is higher, but stability of these materials was not great, yeah. So they show activity that is interesting, but stability was not great. So we can say that from the point of materials itself, there was no significant enhancement. In alkaline media, also we use materials that are state of the art for decades, like nickel oxide mixed with cobalt and iron, yeah, on an anode, and on a cathode also it's nickel-based catalyst. So more or less, maybe to say that on a cathode in alkaline media, discovery of nickel-doped ruthenium oxide was an interesting achievement that, yeah, gave a material that reduced our potential, let's say solid. Yeah, this will be maybe the only thing, but this was also done now, it's almost 30 years ago, yeah, how this is discovered.
So basically there are no major breakthroughs.
No major breakthroughs.
What strategies do you suggest for reducing the cost of hydrogen production to make it more competitive with fossil fuels, from your perspective?
You see, the current target of European Union for 2030 is €2 per kilo, yeah? 2050, €1 per kilo.
You see me smiling.
Yeah, and if you consider now the prices of industrial current and the charge that you need from the Faraday law to produce kilo of hydrogen, from the current price of electricity in Europe, industrial electricity, this is, you would need to have voltage of 0.68 volts, let's say, what's thermodynamically impossible. Voltage is 1.2 volts to split water, 123. So what has to be done? The price of electricity has to go down. This means that photovoltaics has to become more efficient, or this renewable electricity production, or to consider other energy sources, yeah, eventually, yeah, that will make electricity cheaper, but it will be ecologically acceptable, yeah, if we have any alternatives, yeah. But photovoltaics had to, I think now efficiency, if maybe I'm wrong, I'm not dealing with the field intensive, maybe it's 20% efficiency, I don't know, they need to enhance this further. This depends a lot from them. This is one thing. The second, I would say, is to maybe to go in direction of alkaline media more than an acidic, really to remove the noble metals from the picture, because they are available. Most of them, I think, are coming, and platinum and iridium are from South Africa. Yeah, price now, I don't know. It is what it is, but it can be very volatile. You have example of iridium in Corona went 300% up, or you have example of ruthenium in this crisis 2007-8, and ruthenium is also one of the most important technical metals, went to 1000%. Yeah, so it will be good if we can orient on materials that are, let's say, non-noble and more available, cheaper. But the central challenge is the price of electricity. Of course, we can then further play with over potentials in the system in an electrolyzer for hydrogen production. The big portion of it comes from oxygen electrochemistry, so this is essential and fundamental and technical challenge. But if price of electricity doesn't go down, I think if you consider the storage and transport, and yeah, I think on voltage, realistically around 2 volts, yeah, what is today, then electricity should not be more than 2 cents. And this, I think, does not exist anywhere in the world currently. Maybe in Libya, that is the failed state, yeah. So this electricity has to go down. How this economic background of this, is this realistic? How much realistic this is it maybe some nuclear technology is also important to contribute to this in the future, to have cheap electricity, yeah. We'll see, but I think this is the challenge that people from BlackRock said, I think, from this investment fund, that they will not invest a dime in hydrogen before it's economically feasible, yeah. So
that's why they're BlackRock.
Yeah, exactly. So building of infrastructure can be encouraging, but it will not solve the problem of expensive hydrogen production, yeah. So it will be good to have infrastructure that is developing, but the problem of cheap hydrogen the expensive hydrogen production still will not be solved like that. So I think we need to think in a way of cheaper electricity and further improving efficiency of oxygen electron.
How can hydrogen production be effectively integrated with renewable energy sources like wind and solar on a large scale?
If you think about it, when you ask this question, I think on two aspects. One is, let's say, geographically, and one is from the point of the system. Yeah, geographically, you need to concentrate the photovoltaics or production of renewable electricity in an area where you have a sun. Yeah, there was a big project in the past, Desertec, where they want to build massive solar panel parks in the north of Africa, or you have Australia or whatever. Yeah. And then I think the reasonable thing will be to couple this with, to have their electrolyzers on site, yeah. Because I think that combination photovoltaic electrolyzer storage fuel cell it's let's say 4 devices, yeah, or at least 3. But I think this direct photo electrochemical or photo water splitting is very, very inefficient, yeah. So these are really low current density. So I think we need to have photovoltaic and electrolyzer, I would say, on this same location if possible, and then store it and then transport. Yeah, and I think this is something that's already applying in some parts of the world pretty efficiently. Yeah, it works. Exactly.
And finally, what emerging trends and technologies in hydrogen sector are most promising?
But I would say what's attracted my attention, coincidentally, actually, this was already a decade ago, was possibility to operate in so-called acido-alkaline cell. Yeah, I published one paper on that topic. But so thermodynamics in electrochemistry allows you to perform hydrogen evolution in acidic media, yeah, and oxygen evolution in alkaline media. And if you include the bipolar membrane that have parts that exchange protons and parts that exchange OH ions, hydroxyl ions, and you use catalysts for water dissociation, so you could practically have a system that will keep the high kinetics on a cathodic side, because in alkaline media, kinetics is much worse than in acidic, maybe on relevant current densities 100 to 150 millivolts. You need more overpotential in alkaline media, what's a lot. And on the other side, you will kick out the problem with stability of the anode, yeah, in oxygen evolution alkaline media. This is the system that I would focus on. Also, this concept of bipolar membrane can be used for other stuff like water purification, etc. Yeah, it's an interesting concept, the bipolar membrane. But for the hydrogen generation, this is the system I would like to intensify activities. Yeah, I believe that offers some advantages. And there is a paper from 2020 from Sebastian Onner and Shannon Becher. I think Sebastian is now in Fritz Haber Institute. Shannon Becher is professor now in Berkeley. They showed in 2020 that they already reached performance of alkaline electrolyzer, and this is relatively immature technology, but I mean the acid-alkaline cell or this bipolar membrane cell. So it looks that, of course, there's still a lot of space to work on it, but it looks very promising. Yeah, I would say it's a way to go. Yeah.
Aleksandar, thank you for being my guest today.
Arnes, thank you very much for the invitation. It was my pleasure, and thank you for interesting questions. And I hope, we will meet in the future and we'll have time for future exchanges. Yeah.